In this last video, we are just going to discuss how unordered sets or unordered maps are represented in C++. Now, before we actually move on to the C++ representation, I just wanted to emphasize like what is the relationship between a hash table, map, and a set. So essentially, you can think of like I have covered already sets and maps. Maps have like key value pairs, while sets have only keys, and these keys itself are like keys of a map are nothing but a set. Okay, and maps and sets are both like implemented as like either through tree-based data structures, like which are called like ordered maps or ordered sets, or through unordered data structures, which is like hash tables. So hash tables is nothing but it's an unordered, a purely unordered data structure that stores elements in the form of like keys or key value pairs. So both of them are technically absolutely fine. So essentially, whenever we have a key or a key value pair, what we do is we generate the hash of that particular key and store that physically in the hash table. That's how it is. If it is a key value pair, then we again take the key, we generate a hash of this, and at that particular position, we either store both the key and value, or what we do is we store like only the value. So depending on how you're implementing it. So this was an earlier class that I showed you a set class, like you can define essentially what you have like initially is you can have like the array that points to like 100 elements. Like I'm statically declaring it, but that's not the purpose of it. But what you might have in the different functions, like I just wanted to cover one of the functions. So let's say if you are trying to build your own data structure, what you might have is the sequence of events would be like here it might take in a value, or like I think it's better to call it just like a key. And what it might do is you first find the hash of this key, then you reduce the hash to get an index. I'm just telling you the sequence of events. Then you check if the key is like, if there's not an existing key at that index, then you just insert that particular key at that index, or like a key value or whatever. Otherwise, you use a collision resolution strategy, which is like, let's say if you are using like instead of array sets, you're using array set like an array or like a vector of like a linked list. Okay, so in that case you are going to push the value based on your collision resolution strategy. And then after this you might have additional lines of code that will check if the load factor, which is initially, you might also have some more variables here like buckets, number of buckets, okay, number of elements, and whenever you insert a value you might change the number of elements by 1. And the load factor you can check like if the like the ratio of number of elements to the number of buckets is like over a certain factor. You will be doing all of this in the insert function. Then you like call a rehash function that like computes the hash of everything in the hash table and moves it into a bigger function. Similarly, it works for search. In this case, you don't have to worry about rehashing, but you will first have to find the hash of the particular key that you're looking for, and then reduce that hash, check if some value exists at that hash. If that's not the case, then you just return true. If that's the case, like depending on your collision resolution strategy, you write additional lines of code, which is if it is a linked list that is there at a particular index, you might actually traverse that linked list and find if that value exists or not. So here, like I have like a statically defined array, but you can have more complex data structures. That's the gist of it, which is you might have like a vector or something like that. And to end this lecture, I just wanted to recap some of the code that you earlier saw in last week's lecture on unordered maps and sets. So these are both like hash map based, and you can see like if you actually go to the libraries, if you just open your the MinGW or what do you call, like the G++ versions of these libraries, the standard template libraries, you can actually look at the code physically that they have all sort of different parameters. Like let's say they are maintaining a bucket count, a load factor, and max load factor, and whenever they have like they pass a certain value, you can see like the rehashing occurring, which is like, let's say if this one is a hash set, like is a set that is backed up by a hash table or a hash set. In that case, you essentially, like after you add like, let's say 7 elements to this hash table, you'll see the number of buckets to increase by some certain value. So that's the gist of it. And based on these values, like what I wanted to suggest is we almost achieve, like in the best case scenarios, or not in the best case, but in the average case, we would always achieve like a time complexity of 0.1 in like average cases. So that's why like both hash tables or sets and maps that are backed by hash tables, they are like really important data structures and are used for a variety of different problems. So in like almost all cases, you will have like achieve a computational time of almost constant time for retrieval and addition. So that's why like these structures are used in a variety of different problems. I'll end it right here. If you have any questions on any of the videos, we are going to have like a problem solving lecture that's coming very soon. Feel free to bring all sort of questions you have. This is like a really big topic, and you could have like a lot of different strategies for solving like the problems or the challenges that we had, but I just covered the most important ones. But if you read the book, you might be able to find like more strategies or more functions. That's pretty much it. Enjoy your day. Thank you.